Okay, so homework problem 15.7. My handwriting is getting worse. It's a little bit late in the day. My book is in the way. Let's put that here, maybe. Nope. All right, so homework problem 15.7. And this is, the question is, are the eigenfunctions of h hat, of the eigenfunctions of h hat for the particle in a one-dimensional box also eigenfunctions of the momentum operator, px, right? All right, so the momentum operator, you know what? I don't think I ever pointed out to you guys. I'm sure you found it. But in chapter 14, there's a table for these operators. Okay, here's the table. And the momentum operator is IH bar ddx, right? That's the momentum operator. We've mostly been dealing with the total energy operator. Okay. And then there's some other operators that we're going to have to deal with at some point. But we've talked about the potential energy operator, but we haven't done much with it, and the position, right? But we haven't done much with it. All right, so anyway, the momentum operator is minus IH bar ddx. Okay? Good time for you to review these terms and use them in context. Gosh, if you don't use these right, they're going to be nasty. So this is the momentum operator. And it says the eigenfunctions of this guy here. Well, let's look at some specific ones. The eigenfunctions of that, it says for a particle in a box, right? So the eigenfunctions for the particle in a box, for this guy, particle in a box, it's minus h bar squared 2m dx, second derivative dx, this is the total energy operator, but this guy goes to 0 for the particle in a box, right? So it's really just the kinetic energy operator. That's what this is. I'm going to use Ke hat. I think the book uses just E hat with a subscript here that says kinetic. Alright, so this is the operator we've been working with. And what's the wave function we've been working with? Psi is equal to root 2 over a sine n pi x over a. Okay, that's the normalized wave function for a particle in a box. If that doesn't look familiar, you've got some review to do. We've been doing it a lot. And you need to, by the time the test comes around, you need to really hope that that's on there, because it will be. I'm still laughing about somebody saying last week that there were some things on the exam that they hoped wouldn't be on there. I forget who said who I think someone admitted that they said that, but that's just kind of funny. But no, it's all going to be on there. And this one needs to be an old friend. And so does this. The total energy operator, or the particle in a box, which just happens to be the kinetic energy operator. And the momentum operator we've seen a lot less. Alright, so that's how this question starts out. The momentum operator. So let's operate on the momentum let's take the momentum operator, ddx, and operate on this psi and see if and operate on this particle in the box and see if we get, if it's an eigenfunction. N pi x over a. Okay, so we're just taking the derivative of that. Ooh, I see it's not. Because watch this. This is just a constant. So let's pull this out front, right? H bar root 2 over a. And then ddx of that is going to be n pi x. Oops, not x. N pi over a cosine n pi x over a. Wow. Okay, so this is psi. We don't have psi in here that we can factor out, so no. Psi is not an eigenfunction of momentum operator. Big disappointment. I guess more to the point, we've answered the question. No, it's not. Alright, so the next part of the question is calculate the average value of the momentum for the case n is equal to 3. Alright, so the average value of n is, of the momentum operator of momentum is going to be, this is postulate 3, I think. Excuse me. No, it's postulate 4. Okay. So it's going to be psi star, momentum operator, psi dx over psi star psi dx. Now, we know that this is already 1, right? Because we've normalized it. Agreed? So let's take this, and this is going to be that. So the integral psi star p psi dx is going to be root 2 over a sine n pi x over a. This is from 0 to a, right? Times the momentum operator, root 2 over a n pi, sine n pi x over a dx. Okay, so I'm going to take these two terms, multiply them and pull them out front. Becomes 2 over a, 0 to a, sine n pi x over a. And then now I take this derivative first of all, right? Well, I already took that out front. Okay, what's the derivative of that? That becomes, well, I'm going to put this, the derivative of that is cosine n pi x over a times n pi over a. This is dx. Okay, I'm going to pull that constant and that constant out front. So this becomes 2 over a n pi over a times minus I h bar. Alright, 0 to a sine n pi x over a cosine n pi x over a dx. Okay, so what I'm looking for now, I now have a fairly simple integral, and it takes the form, the integral of sine ax cosine ax, because it's got the same argument in there, right? Dx. So let's go look that up. Sine ax cosine ax dx. I'm going to hit the pause button while I go look that up. That's just going to take too long. Okay, so we looked up that integral. And it was minus cosine squared ax over 2a. So let's think about this. I've got too many a's here, so I'm going to rewrite this, okay? This is sine by cosine by dy is equal to minus cosine squared by over 2b. Okay? If that's true, then we can come back up here. You know what? We're out of space here. Okay, so if that's true, then this ends up being, what's that? 2 pi n over a squared, 2 pi n over a squared times minus I h bar, okay, 0 to a sine n pi x over a cosine n pi x over a dx. Okay, we figured out then this integral is what we're trying to figure out. Let b be n pi over a. In that case, then this baby right here is going to come down to be minus cosine squared by, so it's n pi x over a over 2 n pi over a. Okay? Okay. That's what this thing is, alright? So then we also, what we have up front is minus I h bar 2 pi n over a squared. Okay, so then this looks like this here can somehow cancel with that. 2 pi n over a can cancel. But it looks like that other a doesn't cancel. Okay, we'll go back and check that again later. But looks like that, this is going to cancel with that, boom, and boom. And one of those is going to cancel with that. So it looks like we're minus I h bar over a cosine squared, n pi x over a. Okay? So, and this is from, forgot to say this, from a to 0. From a to 0, maybe that's where this is going to come out. It still doesn't come out, does it? Alright, so minus I h bar over a cosine squared n pi a over a minus cosine squared n pi 0 over a. Okay. Oh my. Okay. Well, I'm going to come down here and ask myself, what is cosine squared n pi a? Okay, so I'm going to go to my, this is my sine wave, right? My cosine starts here and goes here. Okay. Well, this is 2 pi. Wait. That's pi. That's pi. And that's pi over 2. Well, that's 0 right there. So at 0, cosine of 0 is equal to 1. So cosine squared of 0 is equal to 1 also. So we're doing this for the third, for 3 pi. It looks like cosine squared of pi is negative 1. Oh, wait. This is a little messy, okay? I'm going to come back here and write it again. Here's 2 pi, and here's pi. So it looks like cosine of pi is equal to negative 1. Cosine of 3 pi is going to equal negative 1. Cosine 5 pi is going to equal negative 1. Okay, so cosine squared, though, looks like cosine squared of, well, I can see of n pi, right? Because it's going to be 1 or negative 1. But it doesn't matter what n is, because cosine squared is going to be 1. I think that's what we're going with this. All right, let's figure out what this is. These A's cross off, these A's don't. I hate this. Okay, hopefully nobody's listening. They got this far in the video to hear me say that. But cosine squared of n pi is just going to be 1. That whole term is going to be 1. Cosine squared of n pi over a, that's a different story. That's a problem right there. That is a problem. Okay, I paused this video because I freaked out. I just got stuck at this point. But there was 2 mistakes that I realized while it was on pause. Number one, there's supposed to be a minus here, it's supposed to be a minus here, and it's supposed to be a plus. And the other one was just obvious, and for some reason I couldn't see. I circled it even before I paused it. But that right there just goes to 0, right? So this is the same thing as I h bar over a. And it still goes, this goes to negative 1, and this goes to plus, because the cosine squared of 0 is 1, right? It doesn't really matter because it just ends up going to equals 0 no matter what, because it's this times 0. Okay, so this goes to 0. It appears to be independent of n. And the question was, what was the question? The question was, show this for n is equal to 3, show it for n is equal to 5. I accidentally ran ahead and showed it for n is equal to anything, and we found that it goes to 0 no matter what. What's this say? How does your result compare with the prediction? Repeat your calculation for n is 5. Alright, so had I done this for 3, I would have put, 3. Had I done this for 3, I would have put 3 in here, 3 there, 3, and so on. But would have ended up getting 0 anyway. And the same thing for 5. So what does this show us for, this is the average momentum. What does this show us, let's see, suggest an expression valid for all values of n, which I did. That's what this is, okay? How does your result compare with the prediction based on classical physics? Well, that's perfect. Because you would expect that if a particle in a box, right, is in a box, you would expect, and you're taking the momentum many times, you would expect your average momentum, because it's bouncing back and forth, right? You'd expect your average momentum to be 0, right? Because half the time it's going this way and half the time it's going that way. So this lines up very nicely with classical physics. However you spell that. Okay. Sorry for the clumsy video. Hope that's helpful.